Welcome back. For the first talk today, we're very happy to have Maggie Miller from Stanford joining us. She's going to talk about knotted handlebars.
Okay, yeah, hi. Thanks for having me participate virtually and still coming to my talk. I'm going to talk about knotted handle bodies. This is joint with Mark Hughes from Brigham Young and Sungwon Kim, who's in Korea. The basic objects in this talk are going to be surfaces in the four sphere. I am a four-dimensional topologist, and I often study surfaces in four manifolds. So today it's just the four sphere, which we could think of as a higher dimensional analog of knots in S3. So just codimension 2 knotting, but in dimension 4. So I think the first question should be, why would you bother studying surfaces in 4D? But if you're going to ask that, then I think you have to justify why would you study knots in 3D. So let's remember why knots are interesting. Knots are interesting because you can use them to describe arbitrary three manifolds through Dane surgery, which means any three manifold problem can be expressed in principle as a knot or link problem. Then you have to argue, why is three manifold topology interesting, but you have to stop somewhere. You can use knots to describe cobordisms of three manifolds. And you can also use knots to study four manifolds by looking at knots in the boundary of a four manifold with boundary and seeing how they interact with the four-dimensional topology, like what kind of surfaces they bound. So you can use knots to understand three manifolds and four manifolds with boundary. Now, if you move up to surfaces in 4D, maybe it's unsurprising to find that surfaces can also be used to describe arbitrary four manifolds through an operation analogous to Dane surgery. I won't explain what that is. We can also use surfaces to describe cobordisms and simplified cobordisms of four manifolds. And we can use them to distinguish four manifolds by maybe looking at a particular homology class in two different four manifolds and showing it's represented by a two sphere in this one and not a two sphere in the other one, and concluding somehow that they're not homeomorphic or diffeomorphic. And moreover, we can use surfaces to understand other structures that don't make sense in dimension 3. So surfaces are interesting for all the same reason knots are interesting, but I would argue even more interesting because four-dimensional topology is very interesting. So some themes for what people study in dimension 4, or at least what I study in dimension 4, using surfaces are giving ways of describing surfaces. It's pretty easy to draw a diagram of a knot in S3 or even in a general three manifold, but it takes a lot more thought to figure out how you're going to describe a surface in a four manifold in order to compute an invariant or say something specific about it. Constructing examples of interesting surfaces is more non-trivial in this dimension, again, because it's so difficult to just draw one in the first place. We can use surfaces to build ambient structures on our four manifolds. Maybe I can explicitly show that my four manifold decomposes as a surface bundle, a Lefschetz vibration, something like that. And then I can try to find ways to distinguish surfaces smoothly when they're equivalent in a weaker sense. So exhibiting this distinction between smooth and continuous topology in dimension 4 through surfaces. Okay, so the basic objects in this talk, I said were surfaces in S4, but the title is knotted handle bodies. A handle body is a genus G solid in dimension 3. This is just another name for this. So just the standard surface, just fill that in and get this three manifold with boundary. So in fact, the basic objects in this talk should be three-dimensional manifolds with boundary. So we're studying surfaces in S4 that bound three manifolds, which is an analog to knots in S3 bounding Seifert surfaces. Okay, so here's 3D motivation for the theorem that I'm going to talk about. Understanding the difference between two Seifert surfaces can be interesting. That's just a claim. So here's a definition. A knot in S3 is the unknot if it bounds a smooth disk in S3. I think this is familiar to everybody. So here's my disk that my knot bounds. But a very perceptive question upon hearing this definition, very reasonable, I've never heard someone ask this just given this definition, is then how many disks does the unknot bound? Does it bound just one or many more? And it's a fact that in S3, if you have two disks smoothly embedded with the same boundary, then in fact, these disks are isotopic real boundary. So in the example on the right here I've drawn, the isotopy is kind of obvious. You would take that red disk and just isotope it to be like sort of flatter and flatter and flatter until eventually it sort of becomes concave upwards and becomes D2. In general, it might take more work to see the isotopy. I could take some green disk that sort of intersects both of these guys. But this is still isotopic real boundary to both the red and the blue disk. And this is a consequence of the three-dimensional Schoenflies conjecture. So if you know what that is, then you can take this as an exercise. But this completely goes out of the window if you move away from disks and go to just even genus 1 surfaces. So even the unknot in S3 bounds genus 1 surfaces that aren't isotopic. So here's two genus 1 surfaces for the unknot. And on this blue surface, S2, I contain a copy of this figure 8 knot, which cannot possibly be isotoped to lie on the red surface. This can't fit. Which means that S2 can't be isotopic to S1. But maybe you should object that, okay, these surfaces aren't isotopic real boundary, but these surfaces also aren't interesting because they're compressible, by which I mean I can find disks in the surface complements that I can use to cut the surface and decrease the genus. So I sort of take my red surface here, it has this disk and its complement, and if I cut it, it will become a smaller genus, so a disk. So then these two disks are isotopic real boundary, which means that even though S1 and S2 are different, they're obtained from isotopic things by a simple operation, this like undoing this compression. So they're kind of like barely different. But it turns out there actually are legitimately interesting Seifert surfaces for one knot. So here on the right, I've drawn two copies of a non-trivial knot. And I went ahead and drew one surface that it bounds in pink and blue. So this surface is like three pink disks glued together along three blue disks in bands. And they're glued in 1, 2, 3, 4, 5, 6, 7 places. So the Euler characteristic of this surface is 6 minus 7, negative 1, as one boundary component. So this is a genus 1 surface. So it's T2 minus D2. So now I'm going to draw another Seifert surface for this knot. I just didn't want to try to fit them both in one picture because like it would look bad. So let me zoom in here. So I'm going to temporarily add two circles. And then I'm going to make a surface. Let's see, I'll start at this pink end and have like pink surface and it'll come through the blue hole. Okay, so that's like sort of a planar surface so far. And I'm going to have it flip over to the back, which is blue, and follow the path of this band tied in a trefoil knot. And then eventually it comes through the pink hole and ends at the blue. Okay, so far I've drawn you a planar surface embedded in S3 with three boundary components, our black knot, the pink circle, and the blue circle. To get rid of those extra two boundary components, I'll just add a tube whose boundary is these two circles. So it will follow the path of this trefoil, sort of engulfing this part of the surface. Okay, so this is a Seifert surface, and I didn't draw it in advance because I think it's hard to look at this picture and know what I mean, but maybe watching it happen makes it easier to see what that surface is. And this is a well-known example. This example appears in Rolfson's book on knot theory, which is my favorite book on knot theory. And these two surfaces are not isotopic real boundary when you identify their boundaries. And they are minimum genus, not compressible, because they're genus 1. And I'll just claim that this is a non-trivial knot. You could compute basically anything about it, and you'd find that it's non-trivial. So these are like legitimately interesting surfaces. Okay, so Seifert surfaces in dimension 3 are interesting. That's kind of three-dimensional motivation, but I'm not a three-dimensional topologist. So from my point of view, it's kind of like unnatural to view surfaces floating in S3. Because from my point of view, when I talk about S3, so here's my picture of S3, I draw it as a plane because it is one dimension down from the preferred dimension, which is 4. And it is the boundary of the four-dimensional ball. So here I've drawn like sort of the lower half space represents the four-dimensional ball. This is just a schematic. And all the surfaces that I've constructed, they have their boundary and their interior inside of S3. And so I don't love this because this is not a proper map. So the boundary is going to the boundary, but the interior of the surface is not in the interior of the manifold. And even if I were not thinking about the four ball, if I were just thinking about S3, then the boundary of the surface wouldn't be going to boundary because there wouldn't be any boundary. It's just like super not proper. But what I could do is push the interior of my surface into the interior of the four ball. So just a very small isotopy, keep the boundary in the same place, and just push the inside down a little bit. Okay, and so now this is a proper embedding. But this can really change like properties of the surfaces that we were studying. So now if I go back up and look at my surfaces S1 and S2 that weren't isotopic to each other, but were also not very interesting. So let me erase this circle. Then in fact, these surfaces are isotopic real boundary in B4. So one way to see that is that, well, S1 and S2 weren't isotopic because of this kind of knotting of this tube that's in S2. So they would definitely become isotopic if I were just allowed to take this place where these tubes cross and change the order of them. So the one that looks like it's in front looks like it's in back. So if I were allowed to do this, then now these two surfaces are isotopic because like I can just sort of unknot that blue thing. But when I have a fourth dimension of freedom, in fact, I actually can achieve that change by isotopy. What I would do is grab this part of the surface that looks like it's in front, and I'll pull it into the fourth dimension, which is not visible in this picture. And then I'll push it backwards and bring it back in the fourth dimension to where I started. And I'll have actually achieved this crossing change. So this is isotopy in 4D. In other words, these tubes are basically one-dimensional, and now they're codimension 3, which is big enough that like we can just do isotopy. Okay, so in fact, S1 and S2 are just completely the same when we push them into B4. And if we go look at our very interesting surfaces, then in fact, these are also isotopic real boundary once we push their interiors into B4. And this is kind of more surprising. These surfaces are like, they look extremely different. You should not be able to visualize the isotopy between them the way that I've drawn these surfaces. There are other systems for drawing surfaces. I sort of said that at the beginning of the talk, from which it is like easier to construct this isotopy, but then you have to like understand the surface. You have to understand surfaces really well in order to do that. So Livingston did this. Like I can't say anything sort of in general, how would you prove two surfaces are isotopic other than try to draw the best picture possible and just produce an isotopy. And maybe that motivates the like following open question, which is really the three-dimensional motivation. So here's an open question, which I learned from Peter Teichner in summer of last summer, I guess. And the question is, does there exist a knot K with two genus G Seifert surfaces bounded by K so that those surfaces don't become isotopic real boundary when I push them into B4? So in other words, is the phenomenon that I just illustrated always true? Like if I have two genus G Seifert surfaces for my knot, do they have to become isotopic when I push them in B4? When I do push surfaces into B4, a lot of the algebraic topology of their complements become the same. The complements will both have cyclic fundamental group, both have vanishing higher homotopy groups. So it's very like no classical invariant can distinguish them. But in theory, the knot floor cobordism maps or the Kavanagh maps or like some linking forms that Friedman uses could distinguish these. But these things are all very difficult to compute, or at least up to the notion of equivalence that you would want. And so you'd have to have an example that you felt really confident in. So actually, I had an example a few days ago. I had two surfaces that I think aren't isotopic when you push them into B4. And they're for a knot with a symmetry, and they're related by the symmetry. And there's some papers about using like knot Flora Kavanagh, where like specifically they show like things don't become isotopic. And so I showed it to one of them, and my knot has 19 crossings, and they're like, we can do 13. If it were 14, maybe in the supercomputer. So I don't know. But I think this is a really cool question. One observation is that if I have my two surfaces, I can actually glue them together to get a closed surface in S4. So I'll just take S1 and S2, and I'll push one of them sort of up in the fourth dimension and one of them down. So up, down, and then glue them together along their boundaries. And if those two surfaces are isotopic in B4, then that closed surface that I get is actually the boundary of a handle body in dimension 4, which sounds like sort of nothing, but maybe is interesting if I tell you that conjecturally it should be the case that gluing together two ciphered surfaces should give the boundary of a handle body. We know this is true topologically for genus at least 2, greater than 2, and it's part of like sort of a well-known conjecture called the unknotting conjecture, which means that no to this question is consistent with the conjecture. But so let's see. I don't believe this, or at least smoothly. Maybe it's true topologically, but I don't care about that. And I think that the answer to this is yes, at least smoothly. Okay, so I guess I'm on record for that. Okay, so that's the end of the three-dimensional motivation. Do you have any questions so far? Actually, I don't even know if I'm able to hear you or not. I think so. I heard someone before. Okay. Okay, so now in S4, let's understand surfaces. Like, what is the unknot? It's a little bit less obvious in this dimension. So a surface is unknotted if it bounds a handle body. So if I just draw like a surface in S3 and include it into S4, then I'll get an unknotted surface of some genus. So these are all boundaries of handle bodies. There is a unique genus G unknot for each genus. So there's this unique genus G unknot because handle bodies are basically one-dimensional. If I have my here's my genus 3 unknot. It's the boundary of this manifold, which is just a thickened graph like this. Great. So any two like genus 3 handle bodies in S4 are both neighborhoods of the same thickened graph. Graphs are one-dimensional. In dimension 4, like the codimension is so big that these two one-dimensional objects have to actually be isotopic. Which means any two genus 3 handle bodies are isotopic, and so are their boundaries. So there's a unique unknot of each genus. But knotted surfaces are a little bit more interesting. Sometimes in this talk, I like don't even bother trying to draw a picture of a knotted surface, but it's kind of like a grad student talk, and this is kind of like fun. So I think maybe it's fun to see a knotted surface. So let's remember, like, how do we draw a knot? A knot, you draw an immersed circle, right? And then at each of the double points of the immersion, you just delete a neighborhood in one of the sheets at the point, and then you get a diagram that you interpret as a knot diagram. And those deleted portions are deeper in the third dimension, right? Okay, so now we're going to do the same thing, but a dimension up. So instead of drawing a circle in the plane, I need to draw an immersed 2-sphere in R3. So let's draw an immersed 2-sphere. So I'm going to draw a surface. First, I'll draw this sort of like light bulb thing. And then I'll draw like the same thing upside down, so like a vase. And then I'm going to connect these two boundaries by like a 2-sphere with its tops and bottoms deleted. Okay, so this is an immersed 2-sphere in R3. It intersects itself in 3 circles like this. Okay, so I'm going to delete little portions of those intersection circles in a neighborhood of each circle, one of the sheets. So maybe I'll delete this neighborhood. Okay, and then I'll do the same thing for the other sheets. So maybe I'll delete this. And maybe I'll delete this. Okay, so now I interpret those parts that I deleted as like deeper in the fourth dimension. And this is really a diagram of a two-sphere smoothly embedded in S4. And the two-sphere that I drew kind of looks like the trefoil. You got sort of like this thing floating around in there, kind of looks like a trefoil. So there, if you've heard of like Verdinger's algorithm that we use to compute pi1 of a knot complement, it also works in this dimension. So if we worked through that, we could check that pi1 of S4 minus this S2 is actually the same thing as pi1 of S4, S3 minus this knot, which is not Z. Whereas pi1 of S4 minus the unknot equals Z. So this two-sphere is strictly knotted. It does not bound a ball. So the problem in this dimension is that really in any sense of the word, just objectively, this particular two-sphere is the smallest non-trivial knotted surface in S4. Smallest isn't well defined, but there is no way you could define smallest and not have this one not be the smallest. And it already like took like a whole preamble to understand what a diagram of it meant, and like it's definitely worse than the trefoil, even though it looks like it. This is called the spun trefoil. So just in general, in dimension 4, if you have like a conjecture about knots, it takes a lot more work to produce an example or understand an existing example. But the point of this talk, which is called knotted handle bodies, which are bounded by unknots, is that in this dimension, we don't even have to care about knotted surfaces. It turns out that unknotted surfaces are interesting. Okay, so let's remember what we asked about the unknot in S3. We asked how many ways can the unknot bound a disk? And the answer was 1. And that was this like cool fact that used the Schoenflies theorem. So again, we could ask how many ways does an unknotted surface bound a handle body? And as a consequence of the dimension that we're working in, the answer is sort of immediately many for positive genus. So here's my genus 3 unknot again, which I've gotten by drawing in S3 and then including it into S4. And I immediately see 2 handle bodies whose boundary is this genus 3 unknot. Because even in S3, there's the handle body that's kind of like the interior region as I've drawn it, and the handle body that's kind of like the exterior region as I've drawn it. So in this left handle body, it's these curves that bound disks into the handle body. And then the right, it's these ones. So these handle bodies are embedded with the same boundary, but they're not homeomorphic rel boundary. So that's like kind of interesting. Obviously that can't happen for disks, but it's also kind of like cheating because at that point, they're not really the same 3 manifold with this identified boundary. So is it really, how interesting is it that their embeddings are different? What we should ask for is how can we obstruct isotopy rel boundary for handle bodies when they are homeomorphic rel boundary, and like really have it be just an isotopy obstruction. This is what we wanted in dimension 3 and didn't exist by the Schoenflies conjecture. And so 2 years ago, there was this awesome paper, Bunny and Goodbye, showed that in fact, in this dimension, there are 3 balls smoothly embedded in the 4 sphere with the same boundary that aren't isotopic rel boundary, which is like completely different from what happened in S3. And this is also related to the 4-dimensional Schoenflies conjecture, which asks whether every smooth S3 in S4 bounds to smooth 4 balls. But it is not like an answer to that conjecture, just motivated by it. This is a really good paper. It's a really long paper. So it's a very explicit construction of the 2 3 balls. It's not just that they exist, it's here's what they are. But it's like I can't tell you in the span of a few minutes what they are. I've seen Dave Goodbye give like an hour-long talk explaining what the three balls are. It's a 100-page paper. If you haven't read it before, good luck finding the construction of the three balls in the paper. But I will say that it's a very explicit construction. So if you do know what the three balls are, it's actually like pretty obvious that they become isotopic real boundary when you push their interiors into B5. So just like before, if I have S4 as the boundary of B5, oh, just wrote 5, B5, then I could take my two three balls and sort of just push their interiors into B5. That's a bad picture, but I hope that makes sense. B3. And when I do that, they become isotopic, real boundary. I drew this sketch as if this means anything of what their three balls look like, where I just hope I'm just trying to convince you how obvious it is that they become isotopic in B5. It's like not a theorem, it's just like a consequence of how they're constructed, which is kind of nice because it matches what we saw with the Seifert surfaces in S3, where they felt very different, but they became the same when we went one dimension up. And so we're seeing that same phenomenon here in dimension 4. Like, I don't know, it's nice when the same thing happens in dimension 4. And another thing is that this construction is very specific to three balls. So I won't really say what it is, but the obstruction is basically that they parameterize a three ball as I cross D2, and they study pi2 of an embedding space of intervals into a certain four manifold with boundary. So that's pretty particular to B3. I don't know what you would do with another three manifold. And I guess nobody knows that you do with another three manifold, and they just posed it as a conjecture that for every genus, it should be the case that there exist genus G handle bodies with the same boundary and that are homomorphic real boundary, but aren't isotopic real boundary. And so their theorem is the genus 0 version, and it's just not clear how to extend their techniques to work above genus 0. So this is what Mark and someone and I proved for genus at least 2. There are handle bodies that satisfy their conjecture. But the weird thing is that our handle bodies don't become isotopic even when you push their interiors into B5, which was not what happened with the three balls. They're constructed in very different ways. And it's kind of like if we compare this to our open question in dimension 3 about the Seifert surfaces becoming isotopic, then we get a positive answer to like the one dimension up version of this, which I think is really cool because it should have been easier to answer the dimension 3 version. Because if you think about it, like to answer the dimension 3 version, we need to distinguish surfaces in four manifolds. To answer this version of the question, we had to distinguish 3 manifolds in 5 manifolds. I think that just sounds harder. It sounds like it should have been harder, but I don't know. I still don't know how to do the dimension 3 version. Cool. So this is the statement of the theorem, just constructing like non-isotopic handle bodies in the 4-ball. And I guess I'll tell you something about the proof in the next 20 minutes. So here's the proof. I'm going to assume, or I need to know, that I have a knotted 2-sphere in S4 that has 2 properties. So here's the first property that I want. I want to know that it is possible to start with my sphere and attach one tube to it to get a torus and have that torus be unknotted. So here's some remarks. I can, or not me personally, but we can unknot any 2-sphere, I don't know why I put quotes, in S4 by attaching some number of tubes. So first I'll prove the same thing for knots, and this is going to look more familiar because the analogous thing for knots is that we can unknot a knot by attaching bands. So let's first see this for knots. So I'm going to draw a knot in a very suggestive way, where I'm going to remember that every knot bounds a Seifert surface. So I'm sort of going to draw the trefoil where I can like really see the Seifert surface. So here's my picture of the trefoil. I'm going to draw it like this. Okay, that went well. Okay, so this is the trefoil, and I've drawn it so that the genus 1 Seifert surface is very obvious, right? It's like this disc with bands attached. Okay, and the claim is that I can unknot this by attaching tubes, which in this dimension are bands, which means that I would attach like sort of a rectangle or some number of rectangles to my knot and get a new knot where I just do surgery along this boundary. So delete where it intersects the band and replace it with like sort of the other two edges. And of course, I can unknot a knot using this operation specifically because every knot bounds a Seifert surface. So what I've just illustrated is I had this genus 1 Seifert surface, and I chose the bands specifically to lie on that Seifert surface and cut it up into a disc, right? So I get a new knot that bounds a disc, and that's an unknot. So in general, if I have a genus G Seifert surface, if I have like 2G bands, I can unknot my knot. Well, it's the same thing with surfaces. Now I'm not going to try to draw an accurate picture because like that would sort of be an exercise in visualization. But in general, if I have a two-sphere, even if I'm not drawing an accurate picture, it's still the case when I have this embedded in S4, it's codimension 2, that it's going to bound a smooth 3 manifold. That's just a consequence of codimension. I think, in fact, you can take that as an exercise too. So here's my 3 manifold. Let's not try to draw that. And this 3 manifold is constructed relative to its boundary by attaching some handles, or we could take like a CW decomposition rail boundary. So that decomposition involves from the boundary some 1 handles or 1 cells, and then 2 cells and 3 cells. So what I'm going to do is I'm going to attach tubes using these 1 cells or 1 handles. So starting from my surface, I'll just attach 1 tube for each of these 1 cells. And I'll be left with like the rest of the manifold, which is just built from its boundary by attaching 2 and 3 cells. And this is literally what a handle body is. It's okay if everybody hasn't seen this before, but a handle body is built from its boundary by 2 and 3 handles. So it's just the same idea, like bands can cut Seifert surfaces up into something trivial, tubes can cut solids up into something trivial. So this first property that I want to assume, it's not that special because I know that my 2-sphere can be unknotted by attaching some number of tubes, but I'm saying I want it to only take 1. Which is like a little bit restrictive, but not that restrictive. Okay. Property 2 is that I want to know that my 2-sphere is not the cross section of an unknotted S3. So you might have seen this term before. I mean that K is not, oh, I wrote the wrong one. K is not doubly slice. So this is something that people study for classical knots as well. I mean, much more in S3. So I mean that if I have my 4-sphere as like the central cross section of S5, so I take 2 5 balls and glue them together along their boundary to get S5. And I have my particular K sitting as the middle cross section of some 3-dimensional sphere. Because K is the middle cross section, I have to know that it can't be the case that this S3 is the boundary of a 4-ball smoothly embedded in S5. And I mean, if you haven't seen double sliceness of classical knots, then this might seem like very difficult to get a grasp on. If you have seen double sliceness of classical knots, then maybe you know that we have lots of algebraic restrictions on classical knots that can prove that classical knots are not doubly sliced. Here, the invariant that we use is the Rock-Lean invariant. So K is the boundary of some 3 manifold in S4, the Rock-Lean invariant, which is like a binary invariant, 8 or 16 of the closure of M3 obstructs double sliceness. So again, I mean, this might sound like sort of an arbitrary condition. Maybe it's hard to obstruct, but in fact, it's somewhat restrictive, but not that restrictive. Like it seems like about half of every 2 knot that I produce, I can just immediately say they're not double slice by using this Rock-Lean invariant. Okay, so I want to know these 2 conditions. And so one problem with 4-dimensional topology is like there is no 2notinfo.org. In fact, I own that website. It's a blank page on my website. But by that, I mean, there's a knot info where if I had a question about classical knots, I had some properties that I wanted to be true, like all at the same time for one knot. The first thing that I would do is go to notinfo.org and do advanced search, like put everything that I want to be true and just like hope something comes out, you know? And then if that doesn't work, I don't know, then I have to like email someone. But you can't do that for 2 knots because there's no table. There's no like general construction. It's really hard to produce a knotted 2-sphere. But on the other hand, there's basically just one family of knotted 2-spheres that people use as all their examples because it's like the only one they can draw, which means that as long as one of those is the example, somebody checked at some point. So I can immediately find a 2-sphere that satisfies both of these properties. I will not explain what the 5-twist-spun trefoil is, but it's a 2-sphere with a name in S4. And it just appeared in 2 papers, or actually like a lot more papers, but in particular these 2, showing that it has both of these properties. So pretty easy to arrange for this to happen. Okay, and now I'm going to construct something interesting. So I'm going to build a 3-sphere in NS5, where this particular knotted 2-sphere is a cross section. So here I'm using my favorite theorem in topology, which is this awesome theorem of Crébert that says that every smooth 2-sphere in S4 bounds a 3-ball into B5. If you're familiar with knots, this sounds wrong because I'm saying that every 2-sphere in S4 is sliced. Sliceness is not interesting in dimension 4. I think that's hilarious. But we actually proved like a better version of this theorem in our paper where, oh, I don't want to say better, this is like a really good theorem, but where we understand like very explicitly how these 3 balls are embedded. And making use of this property that I only need 1 tube to unattach my knot, to unknot my knot, I can actually look at this height function. This is the Morse function on S5. And it's going to restrict my S3 specifically with this number of critical points. So I have a minimum, an index 1 and 2, 1, 2, 3. So basically I'm saying in each of the 3 balls, I have 1 index 1 point and 1 index 2 point. And that comes from the fact that I need 1 tube to unknot my knot. So if you're interested in like the specific construction, like I'm having office hours right after this, but I thought that during the talk, that would be like a lot. But we get like a very explicit Morse function. And at this point, we can isotope RS3, which, oh, by the way, I forgot to mention, look at property 2. We know that K is not the cross section of an unknotted S3, by which I mean like, I guess I also didn't define that. Unknotted S3s in S5, maybe you can guess this, bound B4s. Unknot always means bounding the simplest possible thing. So this 3-sphere has K as a cross section. This is not the boundary of a 4-ball. Okay, so that's the two properties. We used them both. Great. Okay, so now I'm going to isotope my three sphere around. So I know what the critical points of this three sphere are with respect to this height function, and they're not in order. So I'm going to reorder the critical points, pulling the index 1 points down and the index 2 points up. And when I do that, I'll still have the same three sphere. So it's still not the boundary of a 4-ball in S5. But now I've done it so it's like middle cross section is positive genus. It's genus 2. And so really this is a picture of two handle bodies bounded by the same genus 2 surface into two copies of B5. And those two handle bodies are boundary parallel. So even though I'm drawing them in 5 dimensions, I could isotope them to lie really in S4. Okay, so these are not the handle bodies from the example because they glue to S3. So they're definitely not homeomorphic row boundary. This is like a Heegard splitting of S3. So it's more like I have some disks into this handle body and some disks into this handle body. Okay, but I can compare this now to a different and like sort of easier to visualize S3. Oh, cool, I got the colors right. So I have this genus 2 unknotted surface here sitting inside of S4. And here I'll draw the same surface in S4. And I have the same curves on it as well. But now there's just like an obvious pair of handle bodies with that boundary in this picture, with disks in them bounded by those curves, right? So these pink curves bound disks in like the interior handle body, and the green curves bound disks into the like exterior handle body in S3. So I'll really take those two handle bodies together and like sort of push the pink one up a little bit, the green one down a little bit. And I'll sort of get like a similar picture to the thing on the left. But the difference between these two pictures is that on the right, these two handle bodies I literally got by taking like my S3 that I'm including into S4 and taking a Heegard splitting of that. And that S3 bounds a ball. So this is a 3 sphere that is the boundary of a 4-ball. So even though the pictures on the left and right look similar, they're both two pairs of handle bodies, their unions are very different from each other. They're different 3 spheres in S5. And well, the key thing here is that, well, this H1 and this H2 are handle bodies. They could be in S4 that are homeomorphic row boundary. And so are H1 prime and H2 prime. H2 prime. So if H1 and H2 are isotopic row boundary, then it must be the case that H1 prime and H2 prime aren't. Because if both of those pairs were isotopic row boundary, I would get an isotopy from one S3 to the other. But this one doesn't bound a ball, and this one does bound a ball. So that would be a contradiction. Oh, undoing a lot, but it's okay. So we conclude that either the top pair is the example we want, or the bottom pair is. And if I were sort of careful, like when my construction using symmetry, I could argue that they both were. But that completes the proof of this theorem, at least for genus 2. For genus equal to 2, I just constructed a pair of handle bodies that like satisfy the conjecture of Bunny and Gabay, where they were homeomorphic row boundary, but they weren't isotopic row boundary in S4. And I constructed mine specifically starting in dimension 5, so that my obstruction was always in B5. So I also know that they aren't isotopic in B5. I could increase the genus like sort of lots of places in the argument, but the easiest thing to do is the genus G examples come from the G-1 examples by adding a trivial tube. So if I scroll back up to my construction here, I can increase the genus of both of these pictures by just trivially stabilizing the Morse function on these two S3s. So just increase the genus here a little bit. Same thing here. And I have like trivially increased this. So I've perturbed my embedding to introduce a new canceling 1-2 pair. And they're still not isotopic. So either the top halves or the bottom halves are the examples. This is kind of an interesting remark though, because I mean, if you're familiar with this dimension, usually when you have two objects that are very similar, I mean, first of all, like usually increasing the dimension makes them the same. That's really interesting. But also usually stabilizing them makes them the same eventually. So this is like a stabilization operation. But I'm saying like you start with the genus 2 examples and you can add as many trivial tubes as you want and they will never become isotopic to each other, even locally flatly, because our obstruction is locally flat, even when you push into B5. So that's weird. Whoa. Okay. So last few minutes, like here are some very natural open questions. So question 1 is, can you promote this to an infinite family? I didn't emphasize this enough. The Budny-Gavai paper, they can actually produce infinitely many 3 balls that aren't isotopic real boundary. Their obstruction is like much different. They sort of prove like a linear independence of diffeomorphisms. They're studying like really a diffeomorphism group. So they need infinite families. For us, like our invariant was like construct 2 S3s and one bounds a 3 ball and one doesn't. And that's a binary invariant. So we get 2. But maybe you could improve that by using a better invariant of S3s in S5s. That sounds hard because the particular S3s we're using, their complements have cyclic fundamental group. You'd have to use like higher homotopy groups. I said that to someone and they said, well, why didn't you do that? I was like, I don't know how to compute pi2 of an S3 complement in S5. I don't know. And the second, I think, obvious question is, what about the Budny-Gavai conjecture for G equal to 1? So they can't construct solid tori that aren't isotopic real boundary, and neither can we, for 2 very good reasons, like their reason and our reason. But you could still ask, do there exist solid tori in S4 with the same boundary? Homeomorphic real boundary, but not isotopic real boundary. That'd be really interesting. And it's also like a common theme in dimension 4 for the genus 1 case to be like the bad case. So it makes sense that this is the one that's still open. And I think, yeah, I'll stop there. So I have my Zoom office hours are like right after this, and I'll be on Discord.
Could you elaborate a little bit more on, like, you said something like there's a moral that genus 1 is just bad in dimension 4. Could you elaborate?
Well, I guess what I'm really thinking of is this this theorem, which I sort of even mentioned there's 2 things that I'm thinking of. So the first is this theorem of Conway and Powell from a year or 2 ago, where they showed that if 2 surfaces, sigma 1 and sigma 2 in S4 are genus G, or wait, I don't even need to say 2 surfaces. If sigma in S4 is genus greater than 2, I'll say something about 2, with pi 1 of S4 minus sigma Z, then sigma is unknotted. So the genus 0 version of this is the theorem of Friedman. This is a well-known work of Friedman as part of his like proof of the Poincare conjecture. For higher genus, it's like more complicated. And so Mark Powell and Anthony Conway proved this, but they needed to assume a genus bigger than 2 because the proof goes through looking at the complement of the surface and taking some like more subtle information by looking at a linking form that's defined on the boundary of the complement. In genus 2, they just couldn't get the condition that they needed to like prove that it was generic. But in genus 1, I think that like something was like always degenerate, and there was sort of like maybe no hope for doing this technique. So like somehow like local flat unknotting of genus 1 in particular is like the worst case because the boundary is the 3 torus when you look at the complement. There's also like, this is a little bit more vague, but there's a series of papers by Kawauchi that ends with him like claiming to prove the smooth 4-dimensional Poincare conjecture. And there's at one point, like there's been a lot of versions of this paper. I know a lot about this series of papers, but there was one version that he basically claimed that any 2 solid tori in S4 with the same boundary, homeomorphic row boundary, were isotopic. And I emailed him and I'm like, I don't think that's true. And he's like, it's obviously true. And I don't have a counterexample to that. So I would you could do something with that.
If there's no more question, I thank the speaker again.
Okay, thanks. Okay, I'll go. I'll be on Discord or my office hour link. Bye, everybody.
Right. So the one from here to Tampa, okay. The one from Tampa to Houston. Not yet. They say we have 7 days of flexibility. They will do the new flights on this ground. Yeah, I mean there is a flight tomorrow from Atlanta to Dallas. But Dallas is, yeah. No, today there's no flights at all.
There was a flight to Houston at 7 a.m.
Yeah, there was a flight at 7 a.m.